show you how Krake can handle a stateful application. This application is a k-nearest neighbor classification example running in PyCOMPSs. So this is the demo's agenda. First, I will tell you what we prepared in advance. Second, I will show you how Krake is used to schedule the PyCOMPSs application on cluster 1. After that, I will manually trigger a metrics change. This would trigger a stateful migration process in Krake using Krake's shutdown hook. And finally, it is shown how PyCOMPSs migrates from cluster 1 to cluster 2, where the application finishes the process from a saved state. Let's move on with the prerequisites and what was prepared in advance. So first of all, I have set up a Krake instance in the Cloud&Heat powered ASPrint OpenStack. I have also set up 2 Minikube clusters to work with. Also important to note here, in order to register clusters in Krake, we need a standard Kubernetes kubeconfig file. In principle, these clusters could have also been deployed through the infrastructure manager. And in another virtual machine, I have set up a min.io server to store data on. Inside the Krake virtual machine, I also created a static metrics provider. It is called static because it doesn't update the given metric parameters itself. It needs to be manually ingested with new metric data. I also worked on the PyCOMPSs image itself, or more like the PyCOMPSs Krake ready image. So I took the base image of the PyCOMPSs KNN application and added some files to deal with stateful applications, like a shutdown hook script and min.io related Python scripts. Okay, that's it for the prerequisites. Now I will give you a quick overview regarding those terminals down below. The left panel basically acts like the interface for Krake. To tell Krake what it should do, we use Krake's CLI tool called Rock. The top panels show the Minikube clusters. There we will see the application logs. And below those panels are additional panels, each showing a watcher on what pods are spawned on the clusters. Let's check Krake's state right now. You can see what is going on in the left panel. 2 clusters are registered. Currently, there's no application registered in Krake. With Rock Core GMP list, we can see the registered static metrics provider. GMP stands for Global Metrics Provider. Rock Core GM list brings us an overview over the metric. For this demo, we use electricity cost and green energy ratio. Next, we will schedule the PyCOMPSs application with Rock Cube app create. We also use the flag hook shutdown to tell Krake that this will be a stateful migration if the app would be rescheduled. Because the first cluster has a better metric score, due to its metrics weights of the corresponding metrics, Krake schedules the PyCOMPSs app on this cluster. To do that, Krake tells the cluster to pull the PyCOMPSs Docker image to start a pod. We can see the startup of the pod in the watcher of the first cluster. Since it is a stateful app, right on startup it checks for a saved state in the corresponding min.io bucket. But right now there is no data. In the logs of the first cluster, we can also see that the application is already running. In the process itself, PyCOMPSs is continuously saving its current state as checkpoints in the local storage of the cluster. On the left you can see that we now ingest new metric values into the static metrics provider by updating it with Rock. With that done, the score of cluster 2 is raised above that of cluster 1. In the logs, you can also see that the training time was about 35 seconds. The better score leads to Krake rescheduling the workload to the better cluster. The shutdown hook in the app gets the signal and shuts down the running PyCOMPSs application. Now the state of the app is uploaded in the min.io bucket. This can take a while, I cut the video here. In the top right, you can also see some data showing up in the bucket, but that's just a screenshot. Once the data is uploaded, the app requests the migration from Krake. Now the actual stateful migration of the app can happen. In order to do that, Krake tells cluster 2 to schedule the application. The pod terminates on cluster 1, and cluster 2 then pulls the image, starts the pod, and checks for a saved state in the min.io bucket. After that, it downloads the checkpoints. The PyCOMPSs application starts up again, uses the checkpoints, and runs until completion. We can also see that the training time now went down from about 35 seconds to only about 7 seconds. That shows us that everything worked as it was intended. That's the end of the demo. Thanks for watching.